Let's start with our today's DSA journey with this amazing visualizer by dsa.chaicode.com. Use this link to get a 7-day free trial. Let's start with our today's question. Today is our last question from sliding window, and the question is sliding window maximum. Okay, given an array nums and window size k, return the maximum of every contiguous window of size k as the window slides from left to right. Okay, so the question suggests we are given array and a window size k. Okay, these two things. We are given this array and a window size, which is 3 here. So every window of size 3, every window of size 3, every window of size 3, take every window of size 3, everyone, just take every window of size 3 and calculate their maximum. Okay, so let me check. So we have to calculate 3. Okay, so 3 is our window size. So take the first 3, and what is the maximum of the first 3 element? 1, 3 minus 1, 3. Okay, take the next 3 element. Take the next 3 element. 3 minus 1, 3. So in 3 minus 1, 3, 3 is the maximum element. Then again takes another 3, minus 1 minus 3, 5. So 5 is the maximum one. Now, for the next 3, minus 3, 5, 3. 5 is again the 5 is again the maximum one for this. 5, 3, 6. So 6 is maximum one here. And 3, 6, 7. So 7 is maximum one here. So you have to return this in an array. The question, you have to calculate the maximum of the window size. So this is our answer, 335567. 335567. This is our answer. So you are given this array and this window size for every 3 element, for every 3 element, 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 for every 3 element you have to calculate the maximum of that 3 element or k element. Okay, so for every 3 element we have to calculate the maximum or the k. So what could be a solution? The brute force one could become, take the brute force one of this solution is become, take k or take pointer starting from the starting. Okay, take it as I. Okay, a pointer at starting, or just a minute, a pointer I at the starting. Then from I take the next 3 element, calculate the maximum 3. Okay, now I move I to the next element, and calculate the next 3 one. Okay, simply move I to the next one and calculate for the next 3 one. I move I to next one, calculate for the next 3 one, calculate the maximum for the next 3 one. So in this way we can easily, from each point we can take k size of window and calculate the maximum. So write down the pseudocode here, or you can see the visualization here. For every window size k, reports is maximum The obvious approach, slide a window across and for each position scan all k element to find the biggest. Okay. So k is 3, to first take first 3 and what is the maximum? 3. Then again next 3, then again next k size window, then again next k size window, then again next k size window, then again next k size window. Okay. So this is our pseudocode approach of the brute force solution. So we have to scan it every time. So take a function, take nums and a k is our window size. For every element, till n minus k, because after the n minus k we cannot find k element. Simple as that. Simply we can say scan nums of from the I till the I plus k minus 1 or its maximum. Okay. Then simply append max to answer and then return the answer. Yes, we nailed it. So this is our brute force pseudocode. This is our brute force pseudocode. Okay, let me just remove this. This is our brute force pseudocode. Now write, just write down the code. Okay, first take the size. Now take a answer which you have to return and take a starter loop from starting to the end. So this is our loop from the starting towards till the n minus k index. Why? Because after that we cannot get ah. Okay, so this is our code. Here the n is 1, 2, 3, 4, 5, 6, 7, 8, 8. So 8 minus 3 is 5. So 0, 1, 2, 0, 1, 5. So this is our fifth index. Okay. So this is our fifth index. So after that we cannot get 3 element. Okay. So this should be equal to, and how to scan? We actually perform here like this scan. How could we perform this scan? Using another loop for int j starting from I less than I plus k minus 1, or rather less than equal to, because we take k minus 1 here, not k. If we take k, then it should become just less than, not less than equal to. Then simply j plus plus. Here we have to take maximum element. So first take a maximum element every time. So int maximum element, which is nothing but nums of I. Okay, so now maximum element will become max of maximum element and nums of j. Okay, and after we getting the maximum element from each case, so we just take answer dot pushback the maximum element. Okay, and just return the answer. So let's run it and check it. It's work, although we are taking nums of I here. Okay, as a starting of the maximum element every time for the window. So we can easily say at I plus 1, because we already take the ith value here. It should work. Yes, it's working. Let's run it. It should give a TLA because it is a solution. Yes, it's give a TLA. The time complexity is two loops. This loop runs from n minus k. This is for k times. This loop runs for k times. This loop runs for n times. So the time complexity will become big of n into k, and the space complexity will become big of 1. Simple. Time complexity big of n into k and space complexity big of 1. Okay. So now we have to optimize it. And how we can optimize it? Okay, we have to optimize this solution. This is our given array. To optimize it, you can optimize it using a DQ. What is a DQ? DQ is a doubly ended queue. So this could be a DQ. So in queue, in a normal queue, we inside from the back and we get out from the front. This is simple queue architecture. But for DQ, you can insert it from the front or back. Even you can remove element from both sides, front and back. So in DQ, you can do everything. Like you can push element from the back, push element from the front, pull or remove the element from the front or remove the element from the back. So this is our DQ. So how it will help us? Okay, let's understand. Also, we can modify the DQ. So maybe some DQ we want that from the back only insert, and from the front insert and remove both can occur. Everything possible for DQ. So let's just run it again, and mostly I think this visualization will help us here. Okay, so this is our array. I think we don't so much need to see this array. So this is our array. Okay. So this is our array. 1 3 1 3 minus 1 minus 3 5 3 6. Okay. So focus on this DQ. Okay. So this is our DQ. So in the DQ to be specific, we are storing the index of the value. We are storing the index. We will store the index. Why index? Because with this help of index, we can easily get the value in the array. So help of this index, we can easily get the value from the array. Okay. So first, we just store the first element into DQ, which is 1. And we just go to the next element, which is 3. So now we have to ensure one thing every time, that the front of DQ is always the front of DQ always consider the biggest element or the maximum element. Okay. So 3. So this is 1. This is 1 at 0th index. Okay. So now 3. So 1 and 3, which is bigger? So we only store this 0 here. So okay, not the 1. For visualization, it is very helpful. We store the index and the value. So at 0th index, we have 1. So now we encounter 3. So 1 and 3, which is bigger? 3 is bigger, obvious. So we just remove that one. Okay. So let's come here for deco. First we get this one. Okay. So 1 at 0th index. Okay. 0th index have this 1. 0th index have this 1. Okay. Now we encounter 3. So 1 is greater than 3. No. 1 is less than 3. Yes. So which is bigger? This 3. So we have to ensure every time that the front is always maximum. Why? Because we need the maximum element. to be very specific. So it will store 1 and 3. Okay, we only store 1 because with this help, with this index 1, we can easily get the value from the array. Then go to next element. Okay, go to next element. So what is our next element? -1. Is -1 greater than 3? No, just inside -1 after 3. Okay, so now our I or the index says here, just a minute, this one, not this one, this one. So at the starting we have I here, no 1 here. We stored at the first 1, then we goes to 3. We found 3 is bigger. Okay, now we goes to -1 and we store 2. We store this 2 which is -1. Okay, now the I is reaching to the end of the window. Okay, so our k is 3. So now the I is reaching end of, and when we reach end of the window, actually in the front, this is our front, this is our front, this is our back. So in the front we have the maximum element in the DQ. For this window, we have the maximum element. See here, we have 3 already stored here. We have 3 already stored here. So also 3 is our maximum one. So we can easily get a maximum one. Can easily get this Windows maximum here. So same thing happens here. If anyhow it is become greater than k minus 1, answer happened automatically. Okay, so go to the next, which is -3. So is -3 greater? No, so just put 3 which points the -3. Okay, now we got another 3 here because we already reach the I already goes here. I is beyond is 3. I is now at index 4. If we start from 0, I is at index 4. 0, 1, 2, 3. Sorry, I is at index 3. If we take one base indexing, it should 4. So I is at index 3, and we only can take 3 elements. So I is now greater than 3. So we can easily take this element, and insert it and add. We can easily pop back element from the front. We can easily not pop back, we can easily get the maximum element at the front of the DQ. Okay, now we encounter 5. Now we encounter 5. Okay, so for every time check with this. So I is at 5. Okay, index number 4. Is -3 is less than a 4? It's like, is 5 is greater than -3? Yes. So just remove -3. Now, is 5 is greater than -1? Here is greater than this -1. Yes. Remove it. Remove it. Okay. So is this 5 is greater than 3? Yes. Yes, this 5 is greater than 3. So if the 5 is greater than 3, just remove this. And after removing all of this, just enter 4, the index of the value 5. Then go to the next 3. Okay, then we go to our next. Simple as that. Like this is 3 is 3 here, I is at 5. So 5 is greater, we remove this -3. Then we remove this -1, we remove this 3. We insert the 4 and 5. Then we go to, in this window, every time when we reach greater than k, we have to ensure that every time we get them, we extract the front element from the DQ. Why? Because this is our maximum element. So just push it. 3, just push it. And maximum is always 5 here. Now again, when we reach 6, just remove element. Because 6 is the maximum one. 6 is the maximum one here. Okay. Now reach to 7. Okay. 7 is the maximum one. So remove everything and put 7 here. Okay. So in one line, this solution says this line. Just give me a minute. So this is the solution is making sense. The DQ, okay, the DQ store only the useful candidate for the maximum, for the maximum, for the maximum. DQ only store the useful candidate for the maximum. We remove the smallest number because a newer, larger number makes permanently useless. Because we don't need any smaller number, we have to calculate the maximum. So we just remove the smaller number. And we remove old indices because they leave the sliding window. Okay. So every time, so you may wonder that maybe in this window, if this would become 3 and this would become 4, so the 5 will never got out of the index because 5 is bigger, but we are not storing the values, we are storing the indexes, we are storing the indexes. And when we store indexes, when the index 5 comes, it always a 4 get lost. This is our solution. Okay. For that reason, we are using this. The front of the DQ always a maximum of the current window. The front is always the maximum. Just give me a minute. Someone just came. Okay, let's write the pseudocode now. We are taking a function which takes nothing but an array and the window size which is k. For the first few things, we have to take the first we have to take a DQ. Sorry for mistake, which is nothing but we have to take a DQ. And now loop the arrays from the starting to the end index. From the starting to the end. So, and one condition, this is the condition which is actually we have to implement. So when we actually getting a maximum value, we just removing the previous minimum values. And remember one thing, you have to check the indexes, also the value, the DQ. And while DQ means we have to ensure that the DQ is not empty, because if the DQ is empty, we are just pull out the values, this will not work. So while DQ, it means that the DQ is not empty. Also in code we write the full code actually. And nums of DQ dot back, okay, is less than equal to nums of I. If anything, DQ, if anything, so we are removing the element. When we inserting 5 here, actually inserting 5 here, you can easily say we are removing, then we insert 5, or we actually insert 4, which is a index. We actually insert the 4, so we are removing it. So how could we remove it? We just remove DQ dot pop back, simple function. From the back we are removing, so we just take DQ dot pop back, and we have to insert something. So we are inserting the indexes. So I into DQ. So we insert the I into the DQ. So this, yes, insert the I to the DQ. Okay, and if in any condition DQ dot front, the front value of DQ, let's take the bracket because we are actually taking, is become less than equal to minus K. Okay, so it means that we are encounter the range of K, like we have to take first three element and then next time these three element. So first three this element, first three this element, then this three element. So anytime we are encountering this index 2 or beyond, because K is 3 here, we have to check this condition every time, which is nothing but dq dot pop front. Have to check every time dq dot pop front, because if we're not removing the front element, how could we go to the next element? So we are removing the front so that we can go to the next. Okay, if any time the window size is bigger, we have to remove the front also, because the front is the highest of the previous one. Okay, now if I is greater than equal to k minus 1, if any time this happen, then answer dot pushback, answer dot pushback nums of dq dot front. So anytime we encounter a condition, we are encounter a condition where the size of, we reach the size of k in the array. Simple as that. We just take the front element and the front element always carries the maximum because of this condition. Okay, we just take the front element and just return the answer. So this is our solution. Let's evaluate it. Yes, we nailed it. Now just put our solution here. Our solution, let me minimize it. So this is our, and now write the code here for the optimal solution. So take the n, which is nothing but nums dot size, then simply take a deq in C++, deque. You can get a deq. Let's take as deq. So now run the loop from the starting to the end. Starting to the end, just run the loop condition while dq.empty. So this dq.empty actually return that if there's q is empty, it returns true. So when we put not equal to, it only returns true. When if the dq is empty, it will return false. Okay, and terms of dq dot back. So the last element of the dq is actually less than equal to nums of I. Okay, this condition ensured that always the maximum value always go to the front of the DQ. Okay, it always ensure the maximum value should go to the front of the DQ. DQ dot pop back, just take the element back, pop back element, pop back every element. Okay, so now DQ dot pushback. So from the end, not the front, from the end, we have to just insert our index, our current index. That okay, we just remove everything from the DQ. If anything is less the current number, we just remove everything from the back of the DQ. If anything is less than the current number, we just removing this, and we are just push back the current value. Okay, now we have two conditions. If the dq, that front, the current element is become less than equal to I minus k, it goes all actually the window size or the different one. Just pop the front form, q dot pop front. So remove the element from the front, remove the element from the front. If the I is greater than k minus 1 or equal to, what means that if the k is, if the size of window is 3, we have to, the first window always become index 0, index 1, index 2. Okay, so just take this. So this is our array 0 1 2 3 4 and so on, k equal to 3. So the first three element always comes at k minus 1. So if any time the I reaches the k minus 1 or it's greater than k minus 1, it always means we reach our first window or the next window, next window, next window, next window, next window. For every cases, answer dot pushback, nums of dq, that front. So take the front element, take the front index from the DQ, which always stored the maximum value, and then take the value from the nums to actually create the answer, turn the answer, and just simply at the end return the answer. Let's run it. Okay. Hey, a spelling mistake. Let's run it. It works. It works. It works. It will just take a one loop, so the time complexity will become big O of 1, and every dq always store only k element, because our, so time complexity will become big O of n and the space complexity will become big O of k. So this is our question, sliding window maximum. Go solve this question, use this visualizer, use this link to get a 7-day free trial. That's it. Thank you very much.